the answer to a titration question, but it's not exactly a titration, it's more like a mixing of two solutions. A solution of nitric acid with a solid amount of sodium hydroxide. So it's not as though we're mixing solutions, we're actually just adding solid sodium hydroxide to a solution of nitric acid. And now we're looking at the outcome of the reaction. So the reaction, the chemistry is sodium hydroxide reacting with nitric acid to give you water and sodium nitrate. This question comes from your textbook, by the way. It's like problem number 86 from chapter 4 of Brown and others, 10th edition. So the first step we're going to use to calculate the sodium hydroxide amount, the number of moles, is to divide the number of grams by the molar mass of sodium hydroxide. Here's the molar mass of sodium, molar mass of oxygen, molar mass of hydrogen. It gives you a molar mass of roughly 40. 12 divided by 40 is about 0.3 moles of sodium hydroxide. The moles of H plus is given by multiplying the concentration of the solution by the number of liters of solution. You see that liters then cancel, and it gives you moles of H plus. Now, because H plus reacts with OH minus produced from the dissolution of the sodium hydroxide, we're going to subtract this amount from the 0.3, and it's going to tell us how much hydroxide is left over, because obviously hydroxide is in excess. 0.3 is 20 times more than 0.02 or 0.015. And the result is that this number minus the smaller number gives you 0.285 moles of hydroxide. That is present in 75 mLs of solution. So here we calculate the hydroxide concentration by saying 0.285 moles. We'll put moles here. I didn't rewrite the whole number, it's this number. Divided by 0.075 liters gives you 3.8 molar concentration of OH minus. And we're only allowed 3 significant figures, so we're going to write 3.8. We're also asked in the question to calculate the concentration of the other ions. Well, the concentration of nitrate is going to be the same as the amount of nitric acid, the same as the concentration of nitric acid. The solution doesn't change volume, so the concentration of the nitrate anion is still 0.2. The concentration of the sodium cation is going to be the same as the concentration of the hydroxide anion before the reaction takes place. So it's 0.3 in 0.075 liters of solution. So its concentration is 4 molar. By the way, when you want to say state concentration in a shorthand way, you put a square bracket around the symbol of the ion. So that means sodium ion concentration. The last question, part of the question asks what the pH or what the excess of concentration of hydroxide ions is, and whether it's a basic or acidic solution. Obviously, if you have excess hydroxide, it's a basic solution, and I took the liberty of calculating the pOH. pOH is equal to the negative log of the concentration of the hydroxide anion, and it gives you a negative pOH, negative 0.58. You'll cover this a lot more extensively when we do acid-base chemistry. Question 88 asks, and this is what we call a back titration. It's a two-stage experiment, which you would typically see in an analytical laboratory. It says in the question, and it's from page 162 of your textbook, a 1.248 gram sample of limestone rock is pulverized and then treated with 30 milliliters of 1.035 molar hydrochloric acid solution. The excess acid then requires 11.56 milliliters of 1.01 molar sodium hydroxide for the neutralization. Calculate the percent by mass of calcium carbonate in the rock, assuming that it is the only substance reacting with the hydrochloric acid solution. There are two chemical equations that need to be looked at to solve this problem. The first one is that you have calcium carbonate. Calcium carbonate is found in limestone, and limestone is basically a rock that is composed from the skeletons of sea creatures that died millennia ago, sunk to the bottom of the ocean or lake, formed a sediment which then became compacted and it turned into rock. So it's a sedimentary rock composed of the skeletons of dead sea animals. And it's not always pure calcium carbonate. It'll have a high percentage of calcium carbonate, but it has other things mixed in with it. So we had a 1.248 gram sample of rock, according to the question. It was reactive hydrochloric acid, which fizzes when it meets up with calcium carbonate, produces carbonic acid, which turns into CO2 and water, and also calcium chloride. They used an excess amount of the acid, so they used more acid than they needed to cause the rock to dissolve. And then whatever was left over of the acid, they back-titrated with sodium hydroxide. So that's a typical analytical chemistry experiment. You could do a lab report on this, and in fact, that's very typical of what you would do in a university lab report, where you have to write up an abstract, an introduction, materials and methods, results, with a sample calculation. This would be the sample calculation, a discussion of the results, finding conclusion and references. And we'll get a chance to try one of those sometime this year as well. So we're going to start with the back titration. Whatever excess acid that wasn't used was then titrated with sodium hydroxide to see how much of this was not used up. And we're told that 1.01 molar solution of sodium hydroxide was used, and that only 11.56 milliliters of it was necessary to calculate to back titrate the excess hydrochloric acid. Again, the reaction produces water and salt. We know that the number of moles of anything is equal to the molarity of the solution times the volume of the solution used. Here is the molarity of the sodium hydroxide that was used to titrate. Here is the number of the volume expressed in liters. 11.56 milliliters is equal to 11.56 thousandths of a liter. So we found out there was 1.16 times 10 to the minus 2 moles of hydroxide anion used to titrate the HCl, which means there was also the same amount of H plus present. From the amount of H plus that was present, we subtract that amount from the original amount that was here. And where do we do that? We did that here. So the amount of H plus that was reacting with calcium carbonate in the rock is found by subtracting the excess amount from the original amount used. Here's the original amount used. It's this one here. We calculated it over here. Here's the amount that was left over. We calculated that over here. So we subtract this number from the original amount. That's how much acid was used to dissolve this rock. And the reaction is 1 to 2. You see the calcium carbonate, 1 mole of calcium carbonate requires 2 moles of hydrochloric acid to dissolve. So I represented that here. Here's the moles of H plus. Here's the stoichiometry of the reaction up here. So we end up calculating that there's 9.68 times 10 to the minus 3 moles of calcium carbonate in the rock, from which we then calculate the number of grams of calcium carbonate by multiplying by the molar mass of calcium carbonate, which is what we get here. That's how many grams of calcium carbonate is in the sample. The question asks us to find what the percent composition of the rock is in terms of calcium carbonate. So we took that number and divided by the mass of the rock, which was written right over here. And then we multiply by 100. We find out that the rock, the sample, was 77.69% calcium carbonate. Okay, so you can understand why in university they ask you to do a pre-lab. They sometimes won't even let you walk into the lab until you've done the pre-lab, because if you don't understand what the calculation involves, you're going to be floundering around for a couple of hours. So this is a typical pre-lab calculation that you would see in a university level lab report. Are there any questions?